Hello everyone, welcome to Chapter 6, Applications of Integration. This is our final chapter for this course. To kind of recap, in Chapter 1, which was the prerequisite chapter, we reviewed functions and graphs, but we actually began calculus from Chapter 2. Chapter 2 was on limits, Chapter 3 was on derivatives, Chapter 4 was on applications of derivatives, Chapter 5 was integration, and Chapter 6 is applications of integration. So it's really very limited in terms of the concepts, but we went deep into each of these concepts in these chapters. So in that sense, we've really covered a lot. So when I say simply derivatives, we looked at derivatives from different angles, isn't it? We saw it as a slope, we saw it as a limit of dq, then we saw it through the rules, the differentiation rules. Then we saw it as the slope of the tangent line, and then we saw it as a rate of change, and then all the related rates, implicit differentiation. So you can see how deep we went in just that topic called derivatives. We also did something like that to integration, and now we're looking at applications of integration. So we begin with areas between curves. Let's start with the definition. If f and g are continuous with f of x greater than or equal to g of x throughout the closed interval a to b, then the area of the region between the curves y equals f of x and y equals g of x from a to b is the integral from a to b f of x minus g of x dx. It's really not complicated, but it's kind of wordy, so we might find it a little challenging. So to help you here, let me give you a visual of this. Let's say this is y equals f of x. Okay. Let's say you are talking about this closed interval a to b. Okay. So f and g, so this is my g. So this is y equals g of x. Now we'll go back to the definition. If f and g are continuous with f of x greater than or equal to g of x. I know that because f of x is happening above g of x. Okay, so to help us understand that, I'll call this the top function, and this g of x is happening below it, so that's going to be my bottom function. Then the area of the region between the curves, that means it must be this area here, right? So this is between the curves. And previously we saw area that went up to the x-axis. So we simply called it the area below the curve, or area under the graph, under the curve. So when we say under the curve, we know it automatically went up to the x-axis. But here it is between these two curves. So the area of the region between the curves is f of x is integral of f of x minus g of x dx. So you're taking the difference of the two functions to find the area in between them. Very intuitive, isn't it? And so you can kind of see that this is nothing but it makes sense, because if you take just the purple graph, right, f of x, the area under the curve for that would be how do I show this? Okay, I'm going to show it to you like this. It would be this entire one, right, under the curve. And for the area under the curve for the purple would be this. So if you did the whole thing for f of x under the curve minus the whole thing under the curve for g of x, the resultant area would be in between, which is the yellow shaded region, isn't it? And that's what we're trying to show you here in through this formula. So then what happens is, I can say, just to make it easier for us to understand, area between the curves is the area between f of x and g of x. F of x is greater than g of x because it's happening above it, and also meaningfully, the area under the curve for f of x will be more than the area under the curve of g of x. Right? So which means this is the area of the top function minus area of the bottom function. when you do this, it automatically implies that the area will always be positive. And this is important because we've seen areas that are negative in the net area situation. This is guaranteed because you're doing the larger area minus the smaller area. That's why we started off by saying f of x is greater than or equal to g of x. And so what we're saying is, well, area of the top function, right? Area under the curve from a to b, f of x dx minus integral a to b. This is the area for the bottom function. And this can be brought together from our, the properties, the difference property of integrals as f of x minus g of x, because they both run over the same interval. And that is our definition. Okay. So it's very intuitive, so you can see that. Now I'd like to work through an example and show you different ways to approach the solution for this problem. Okay. So here is a warm-up problem for that. It says, find the area of the region enclosed by the parabola y equals 2 minus x squared. Even if they didn't say it's a parabola, we know it is. But they're being very descriptive here, and they call it the parabola and the line. Y equals negative x. Okay. It's 2 minus x squared, so you know your graph will be facing down, right? It's a parabola that's pointing down. And y equals negative x. Y equals x squared, y equals x would be like this, but if it's negative x, it's going to go down like this, right? So I want to just sketch this, and I will show you an actual good-looking graph. So I know that this is going to be something like this. And then we have this one going, oops, it has to go right through the origin. So then this is where it's from here to here, that's where they meet, right? So it has to be this shaded region. So I'm able to visualize this. Now if you think of this, you can, just to give you a quick recap of the origins of area under a curve. So the origin was that we took the area, the region, and we sliced it up into thin rectangles, and then we took the area of each rectangle, added them up to get the approximate or the estimate of these of the area. And so we did it by left end approximation, right end approximation, or the mid rule approximation, whichever method we used. We basically used the Riemann sum. When we took the limit of the Riemann sum, that gave us the integral, that gave us an exact area. Okay, that's the origin. Here is a better looking graph. So it looks very much like the way we sketched, right? Now the idea is, we saw that when we pinched these two ends, right? I said this and this. We know that that is where you can enclose the area between the two curves. So what are those 2 points? Now this graph gives us those points, but how do we find those points? Okay, because when you use your graphing calculator, it will give you these points and making it easier for you to figure that out. But how do we really algebraically find these points? Well, we can find them simply by setting the two equations equal to each other, because these are nothing but the points of intersection. So your graph cuts through each other at 2 places, isn't it? So because if they were both lines, then they can only intersect at 1 point, or if they're coincident lines, then they will intersect at every point, right? They're coinciding lines. But here, one is a parabola and the other is a line. So the parabola kind of makes a U-turn and meets it again at a different point. So you have 2 points of integration, 2 points of intersection, and that can be found algebraically by setting the 2 equations equal to each other. So then I'll say, let us set both equations equal to each other, now we need to do this so that I will know from where I have to go for a to b, isn't it? Because that's what will give me a to b, and then I can do the integral a to b, the top function minus the bottom function. We can easily see what the top function and what the bottom function is. What we can't see is those endpoints. And so when I take the first equation, which was 2 minus x squared, the parabola, and I set it equal to the line, which is negative x. Y equals this and y equals this. Set them equal to each other. You know it's going to be a quadratic equation. So bring them all to one side. I'm going to take them all to the right hand side so that this negative x squared will become a positive x squared. So that means I have x squared minus x minus 2 equals 0. Okay. As always, factorize them. That will give us x plus 1 times x minus 2 equals 0. Through zero factor property, set each factor to 0. We get negative 1 and x equals 2. These two give us the limits of integration. That's very important. The points of intersection actually gives us the limit of integration. And what's neat is you really don't have to find the y coordinate. You just need the x values, because that will be your a and your b. And now we're ready to find the area. So area is area between the curves, that is a to b, f of x minus g of x dx. And here a is negative 1. It's always small to large. So negative 1 to 2. Because what if you did, when you factorized it, you put x minus 2 and then x plus 1. You would have x minus the 2 first and the minus 1 next. You still have to adjust it so that the smaller number is your a and the larger number is your b. Right? So that is there. That's your top function minus the bottom function. And the top function is your parabola. So write the parabola, 2 minus x squared. Minus the bottom function is y equals negative x. Notice that there is double negative there. That's going to be 2x minus x cubed over 3 plus x squared over 2, and apply the limits here. So that's going to be top limit minus the bottom limit that's cubed. Top limit minus the bottom limit. Of course, I will let you compute it. I'll just put the numbers though. Okay, just checking. Minus negative 2 plus 1/3 plus a half. Okay. Pause the video, do the computation. So this should be a 10 over 3 minus a negative 7 over 6. Clean that up. 27 over 6, which can be reduced to 9 over 2. And that's your answer here. The area between the two curves is 9 over 2. Okay. Now, if they gave us the units, then you'll know, what the area is. 9 over 2 square meter squared, or whatever the problem is, the real life application of the problem is, then you will attach the units based on that. So this is a warm-up problem. So now let's go to another problem where we will look at it in different methods on how to handle it. Find the area of the region in the first quadrant that is bounded above by y equals x square root of x and below by the x-axis and y equals x minus 2. Okay, first quadrant. So a quick sketch. I'm going to show you a better graph, but let's do a quick sketch. Y equals square root of x, you know that's going to be like this, right? Square root of x. And bounded above and below by the x-axis, so you got the x-axis right there, okay, x-axis, and y equals x minus 2. Well, y equals x is the line that passes through the origin. You know that we just did that. We did the y equals negative x actually. So y equals x will be positive slope, and it's like a 45-degree line through the first quadrant. Now if it's x minus 2, you know minus means you move to the right from transformation, so that means it's going to move 2 places to the right, and so my line will look something like this, right? Y equals x minus 2. So this is going to start at 2. Right? That's our x-intercept. So that's our 0 there. Now we need to find this area. Okay. Here. And to do that, we're going to try in 3 different ways to do this. Okay, 3 methods to do this. So how do we handle this? The difficulty here actually is that you do not clearly see the top function minus the bottom function, because you see the top function, no problem, but the bottom function, you have 2 of them. You have a line here, the x-axis, and you also have a line here, y equals x minus 2. So because of that, it's kind of challenging to see which one is the top function, which one is the bottom function, right? So let's start with method 1 and then see how we can use method 1 to help us find the answer. So here is the better looking graph I was talking about. So your blue blue curve I should say, is your y equals x square root of x, and this yellow one is your y equals x minus 2. The approach here is to divide this region into 2 parts. Okay, so there's region A, which is the orange region, and you're kind of breaking it where your x-axis kind of ends, and it ends where the yellow line begins. And so we kind of break it into 2 parts. So this orange region and the blue region. So the total area between the curves, or this shaded region, is this region A plus region B. And in region A, you have very clear understanding of going from 0 to 2, okay, 0 to 2, top function, which is this blue function, minus the bottom function, which is your x-axis. The equation for x-axis is y equals 0. So that's very clear. If you go to the B region, the blue region, you do have, again, top function, which is still y equals square root of x, minus the bottom function, which is the yellow function, which is y equals x minus 2. And you know that it goes all the way from 2 to 4. We're going to use algebra to help us to know that it's ending at 4, because we need to find where they meet, right? So we have to set the 2 equations equal to each other to see where they meet. Because I used the graph already, I'm able to show you where they meet. So I don't, I feel bad that that information is out already. Never mind. So the whole idea is I want to do 0 to 2. Oops, that was supposed to be top function minus bottom function. I'll skip the dx for now. Plus, for the B region, we are going from 2 to 4, top function minus the bottom function. And I'm getting all this from the graph. I'm going to do all this algebraically actually. Top function is the square root of x, and in this case the bottom function was x-axis. Here top function is square root of x, and the bottom function is the line. Alright, so that is the general idea. Now let's go ahead and find the limits of integration. we need to find the limits of integration. Okay, now we need to figure out where these two meet. Okay, so this implies I set the square root function and the line equal to each other. Okay, so we want to know where they meet. Square on both sides, so that's going to be, show that square. So x equals x minus 2 the whole squared, x squared plus or minus 4x plus 4. Okay. A squared minus 2ab plus b squared. And then bring all of the terms on one side, so you get x squared minus 5x plus 4 equals 0. This implies you have x minus 1, x minus 4. Set each factor to 0, you get x equals 1, x equals 4. Okay. Now if you look at, again, this is going back to algebra. In algebra, there was a reason why we tested or checked our solution. Remember that? It was true with square root functions, particularly with rational functions, logarithmic functions. These were three specific ones I can think of right now, where we must check our solutions to look for any extraneous roots. Extraneous roots would be answers that look fine here, but they are outside the domain. They're extra. They're outside the domain, which means they are not in the part where we are focusing on. So here, first of all, you know that all this is happening in the first quadrant, and we also know that y equals square root of x happens only in the first quadrant, but we need to check the solution. So if you check the solution, I plug in 1 for x. Okay, square root of 1 equals 1 minus 2. Okay, I'm checking it for the two solutions. So let me first focus on the first solution. That's going to be 1. Square root of 1 is 1. 1 equals negative 1. 1 minus 2 is, look at that, right there it is a false statement. Let me check for 4. Sometimes you can have both of them failing. Okay, that's also possible. So that's going to be 4 minus 2. Right? In the original one, square root of x equals x minus 2. That's where you substitute. So that's going to be 2 equals 2. This is good. That means your x equals 1 is an extraneous root. If you did not check this, you will be using 1 to 4 blindly as your limits of integration. So this is kind of challenging because you really want to make sure that you are checking here, just because of the algebraic nature of these kind of solutions. They can be extraneous roots. So you want to always check to see which root really works. And we know that only the x equals 4 works, which is also supported in our graph, because x equals 1 would be somewhere here, and you clearly can see that it doesn't meet. The line does not meet the square root of x, the curve. So the line and the curve, they meet only at this end, not in this, on the left end. And so it's verified on the graph. It's also verified when you did it algebraically by checking the solutions. Okay. So anyway, checking the solution gave us that information, and so we have to consider the area between. So then I come back and say, since we are asked to consider the first quadrant, this isn't the problem, quadrant 1, we look at the area between the curves from A to B, where A is 0, let's say A to B, which is 4, the value we just found. We can take a look at the graph here and say, okay, we have decided to go from 0 to 4, right? Because it's the first quadrant, we start at 0. it said 1 to 4. 1 came out as an extraneous root. So we only had the end point as 4 on the right end, but for the left end we chose 0 because of the first quadrant. Now because of our approach, we now take a break at 2, 0 to 2, and then from 2 to 4, right? This top function minus, so I'm coming back to this total area. So let's write that out here. Total area will be integral 0 to 2 square root of x minus 0 dx plus, just to give you a quick heads up, this was our top function and this was our bottom function. This bottom function is nothing but your x-axis, that's why it is y equals 0. And then we went from 2 to 4, and that was square root of x minus the line was x minus 2 dx. Once again, this was our top function. This always dominated, so we had no problem with identifying the top function. For the bottom function in the second half, we clearly have the line as the bottom function. Okay, all good here? 0 to 2 square root of x dx plus integral 2 to 4 square root of x minus x plus 2 dx. Now it's a breeze because we just have to use, and these are all easy ones, so no worries about substitution method, use substitution, things like that. So 0 to 2, again just for convenience I'm putting them all as the power. That will be x power 3 over 2 over 3 over 2, 0 to 2, plus x power 3 over 2 over 3 over 2, minus x squared over 2 plus 2x, 2 to 4. So this will entail a lot of terms. That's fine. So here I'm going to just do 2 power 3 over 2 minus the 0 power 3 over 2. I'm just to avoid too many terms, I'm not going to enter that. Plus, here you have 2 over 3 times 4 power 3 over 2 minus 4 squared over 2 plus 2 times 4, right, all this, minus 2 over 3 times 2 power 4 over, getting mixed up. Okay, that's better. Minus 2 squared over 2 plus 2 times 2. Close it and the bracket. Okay. Here it's 1, right? So 2 power 5 over 2, you're going to get that. Don't try to reduce it any further yet. When the time comes, you can start doing that. So I'm going to kind of write out all the terms, because here again, you actually will see that this is 16 over 2, which is 8. Okay. Let me see if I can insert something there. So this is going to be a negative 8, and this is going to be a positive 8. So these will actually go away. So wherever you can see them in action, take care of them right there. Let's do that. So sometimes, because of the inking process, I think some terms tend to disappear just because of the Wi-Fi and all that. So don't just rely on my screen. I hope you're doing it at your end, so you can always pause the video and track it with me. There were times when I've seen, not this problem, but previously in other videos too, a minus would be missing. Even though I wrote it the first time, it would be missing 2 steps later. So that's something we have to contend with in terms of technology sometimes. But if you do it on your own, I'm sure you'll be able to handle these kind of things much easily and won't be confused. Okay, likewise here I have 4 over 2, which is negative 2, and this is plus 4. They don't cancel off, but I can see that it reduces differently. Okay. So that will be 16 over 3. Those go away. Then I have a minus. This will be also a 2 power 5 over 2 over 3. And then negative 2 plus 4 will be, hold on, this is a minus here. So minus, so that will be a plus 2, but with the minus outside, that will be a minus 2. Okay, sorry, I was talking to myself there. Alright, now we can cancel these off. Let's go away. And simplifying this, 16 minus 6 is 10, 10 over 3. Okay. Now that was our method 1. So method 1, we broke it into 2 areas and were able to see it very, very clearly. So before I go to method 2, I want to introduce another concept and then use that concept for method 2. Okay. So the concept is again not too strange. It's just that I'm asking you to look at it from a different view. Now we've been looking at top function minus the bottom function, right? Now in this example here, bottom would be like this. X-axis is very specific, is very clear. Bottom function is very, very obvious to see. But if you look at this line doesn't look like bottom. It looks a bottom function because you had a blue curve on the top. It looks more like a function that's to the right, not at the bottom. So if we have those confusions, is there a way to see this from a different view? And that's what this concept is going to teach us about. So long we've been integrating with respect to x, right? Because it was all about top and bottom was always in respect to x, isn't it? The x-axis was kind of a reference to know which is bottom and top. So we can also integrate with respect to y, and that's the concept I'm trying to explain here in the next part. Now, integrating with respect to y means you are now looking in terms of the y-axis. Y-axis is now your reference. So it's as if you rotated it sideways. You can actually look at this graph sideways and it appears like what we just did in terms of x. But now in terms of y, what is top and what is bottom would now become what is right and what is left. So what is to the right, okay, that function will be bigger than the function that is to the left because you have accumulated more area as you move to the right, isn't it? Because your number line increases from left to right. So here we are talking about the area between the two curves. So you have the blue curve and you have the yellow curve. The yellow curve is bigger than the blue curve. So the area between the two curves would be the, as you can see the formula here, the area of the right function minus the area of the left function. So right minus left will give you that. So we have 3 different cases here, okay, 3 scenarios. The first scenario, the two curves don't meet, but you are given the limits of integration, right? In the second case, they meet at one end, but not at the other end, but we do have the limits of integration because we need to know where we want to go up to. And in the third scenario, they meet at both ends. That automatically gives you the limits of integration. So here, we're talking about integrating with respect to y. So that is going to be the right function minus the left function. And notice how we had the variable of integration to be x. It was dx. Here it's all in terms of y. So the whole idea of writing the equation also will be rewritten in terms of x. So we always write y equals x minus 2, right, for instance. But here you'll have to say x equals y plus 2. So you have to rewrite everything in terms of x so that it's all the x's are written in terms of y so that everything is with respect to y and not x. So now let's look at the other method. I'll just say we can solve the above example, above meaning not just this one but the example we did previously, by integrating with respect to y. So that becomes a method 2. Method 2 is, can you see it as the right function minus the left function? Okay. So I'll put up the graph again. Here is our graph. And notice there that we didn't divide this into 2 regions like we did there, right? A and B. So you see it all as one blue region, because we're seeing it with respect to y, and so you're looking at the right function and the left function, so the bottom function really doesn't bother us. Now what happens is, I should say, instantly you notice that your functions are rewritten in terms of x. X is equal to y squared, because there it was y equals square root of x, right? Let me write that here. Y equals square root of x. You wanted to write everything in terms of x, so you had to square on both sides, so y squared equals x. And that's why you have x equals y squared. And the other one was y equals x minus 2, so you solve this for x. So x equals y plus 2. And that's what you have here and here, right? You've rewritten everything in terms of, let me clear this, in terms of x. Okay, so if you are again thinking about the origin of the area under a curve, in this case area between these two curves, if you're doing this with respect to y, you have this red rectangle here, right? This is giving you a perspective of how you're slicing up the area. We've sliced them vertically in previous examples because we always did them with respect to x. But when you're doing it with respect to y, your rectangles are sliced this way, right? So your rectangles are horizontally sliced, and so this is one slice of a rectangle, an enlarged version. So you can see the width and the length, right? All right, so we have this, and let's see how we can solve this. Now we need to find the limits of integration, and this time with respect to y, isn't it? Let's do that. Oh, just before that, I want to give you this quick connection here. So when we did integrate with respect to x, right? With respect to x, x means top minus the bottom. What we did was, we got the limits and we did top function minus the bottom function. And it was dx because it was with respect to x. When the limits of integration was the left limit, right? Left end of the shaded portion to the right end. So I just say left limit to the right limit. Okay. And what we do when we do the integration, when we integrate with respect to y, is that because it is y, you no longer have top and bottom, you rather have right and left. So it's right function minus the left function, and because it's with respect to y, it is dy. But then the limits would be bottom limit, right? Because you're trying to see the region from the bottommost to the topmost. So this would be the top limit. See how they're all coming together? Top, bottom, left, and right. So as you can see here, right? So this is the bottom limit, and this is the top limit. So C to D. So bottom, the shaded region, you're seeing the lowest part to the highest part. Okay, that was something I wanted to insert in before I forget. I think now we're ready to actually do the problem. So we need to find, so I'll just say rewrite, I'll use a different color. We rewrite the given equations in terms of x. So I already showed you that. So we now have y equals square root of x is now rewritten as x equals y squared, and y equals x minus 2 is now rewritten as x equals y plus 2. We need to have this in the form so that we could find the limits of integration. Remember, it's all with respect to y, so when you set these two equations equal to each other, your answers will be in terms of y, and that makes sense. So y squared minus y minus 2 equals 0. That's going to be y plus 1 times y minus 2 equals 0. Y is negative 1 and y is 2. So you go from negative 1 to 2. That's what this means. But if you looked at our graph again, remember that this is negative 1. Negative 1 would go all the way down here. Negative 1 to 2. Negative 1 to 2. 2 looks good, but negative 1 is outside our focus. Our focus was only the first quadrant. This goes into the negative part of it. So we will kind of rule out the negative 1. Okay. Outside quadrant 1. Which means we're going to start from the first available point, which will be 0, right, for the first quadrant. So it will go from 0, that's where the shaded region begins, 0 all the way to 2, the bottommost part of the shaded region to the topmost part of the shaded region. Okay, this implies we start at y equals 0. Alright, and then we go back to y equals 0 to y equals 2. And so area will be 0 to 2, bottom limit to top limit, right function minus the left function, all in terms of y, so dy. 0 to 2. So let's go to the graph again. The right function, the rightmost function is actually your line. The line is y plus 2. So the right function is the yellow minus the left function, which is the blue, which is y squared. Let's write that down here. Y plus 2 minus y squared dy. So again, for our quick reference, let's say that the right function is the line and the left function is the square root of x. Okay, a square root of x for our understanding, but you know we're not calling it square root of x, we're calling it y squared. Okay. Which is y squared here. Okay, that's better. Y plus 2 minus y squared dy, then it's regular integration, y squared over 2 plus 2y minus y cubed over 3, and limits of integration 0 to 2. Top limit minus the bottom limit. Again, I don't want to do this, but I don't want you to think that I forgot about it. I just don't want to do it because I know it will be a 0. Alright, so that's going to be 2 plus 4 minus 8 over 3, and that comes back as 10 over 3. Okay, same as the other example. Same as method 1. And you can see how quick this was, because you didn't have to worry too much about breaking the region and kind of doing the problem twice, right? Because you're doing the area, finding the area for one portion plus the area of another portion. We took care of that by turning our attention to the y-axis and said, okay, let's integrate with respect to y-axis, and that took out 2 separate integrations and helped us to get it with just 1. Well, definitely we were able to find the result with less work. We are happy with that. In fact, there is a method 3. Method 3 is not going to work always. It just depends on the setup. And method 3 basically uses the idea of geometry and uses that to kind of come out with the answer in a quicker way. Okay, so let me get the graph again. So the method here is that we will take the area of this whole region, yeah, which is the area under this curve, right? The whole thing, 0 to 4, this whole thing under the curve, that minus this triangular region, right? So this triangular region can be found using algebra. So if we did that whole thing, the area under the blue curve, minus this triangular region, that will give us the blue shaded region. That is the approach here. Again, as I mentioned, this will work only if you had such a geometric setup nicely working. If it doesn't, then this method 3 would not really be available for us. Okay, so that's going to be area is area under y equals square root of x from 0 to 4, okay, all the way, minus area of the triangle, the yellow region. That's our focus here. So area under the curve would be very, very straightforward. 0 to 4, square root of x, because that's the one thing that goes all the way, 0 to 4 dx, minus area of the triangle is half times base times height. So that's going to be half times base is from 2 to 4, right? That's where the line begins. So 2 to 4. So 2 would be, 2 to 4 would be 4 minus 2, the difference in their length. So that's going to be, I'll just say 4 minus 2, which is 2, times the height. The height is, plug in for 4 in your function, because that's where the yellow and the blue meet. So if you plug in for 4 at the function, you get it as 2. The square root of 4 is 2. Because they meet at that point, you can also plug it for the line. The line is y equals x minus 2, right? So if you plug in 4 for x, 4 minus 2 is 2. So it's going to work either ways. So that's there. That's x power half plus 1. So that's 3 over 2 over 3 over 2. 0 to 4 minus half times 2 times 2, which will be 2. And that's going to be 2 over 3 here. 4 power 3 over minus 0 power 3 over 2 minus 2. 4 power 3 over 2, we've seen that that's going to be 8. 8 times 2, 16 over 3 minus 2. That's going to be 10 over 3. Same as method 1 and 2. Okay. So what's really neat is that you do have various ways to look at a problem, and as long as it's mathematically valid, it's using calculus techniques, you are totally fine here. And here we did use calculus, but we also used geometry in method 3, which is perfectly fine. That's the whole idea of going into higher levels of math, where we are free to use all the knowledge from our past. It's like a toolbox. You search through your toolbox and use the right tool or a combination of tools to get your answer. So I hope that was enjoyable, that particular problem, because it really gave us different views and helped us to figure out that we got the right method each time, because we got the right answer and pointed to it. Let me wind up with this particular problem type, where we'll try to integrate with respect to x and with respect to y, so it gives us a better appreciation of the given problem. So I'll say find the area of the region between the curve y equals 3 minus x squared, figure out what that is, what shape that will be, and the line y equals negative 1 by integrating with respect to a x and b y. Okay. So do a quick sketch. The sketch should be this is 3 minus x squared, so it is x squared minus x squared will be like this, right, facing down, and 3 would be 3 steps up. So I'm using transformation to draw that graph. So that's going to be y equals 3 minus x squared, and y equals negative 1 is a horizontal line that passes through negative 1. Green, that they look alike, those colors. Use a different one. Y equals negative 1. And that's it, you're trying to find this region. And one with respect to x and the other one with respect to y. And do you think it's possible? Think about it. Is it possible to do it in both ways? Certainly. Right? Again, a quick recall. With respect to x means you do top function minus bottom function. With respect to y means you do right function minus the left function. So we need to figure out what is what. Okay. Now, if you're using this kind of sketch, it's always helpful, and you always want to see where will this meet, right? Just to know where will these are the points where they will meet. Well, this is the point where the purple and the pink meet, these two, but this will be their x-intercepts. So it's good to have all those details as well, just in case. Okay, let's begin with the first part with respect to x. So we need to find the limits of integration. Because it's with respect to x, we can use it the way it is. So you have y equals 3 minus x squared and y equals negative 1. Set them equal to equal to each other. Because it's simple here, I can move this to the other side. So it's going to be x squared equals 4, which means x equals plus or minus 2. Okay? That means your left end a is, when we do with respect to x, we call them a to b. When we do it with respect to y, we call it from c to d, just to help us to reorient our direction. Okay? So a will be the smaller number, negative 2, and b will be the larger number, 2. Okay? So then our area will be negative 2 to 2, top function minus bottom function, dx. So top function is the purple function, which is a parabola, 3 minus x squared, that minus the bottom one. So negative 2 to 2, 3 minus x squared, minus, the bottom function was this horizontal line, right? Horizontal line is negative 1. So it's negative 1 dx. Negative 2 to 2, 3 minus x squared plus 1 dx, which is basically 4 minus x squared dx. Okay, it's time to integrate. 4x minus x cubed over 3. This whole thing can go from negative 2 to 2. This is top function minus bottom function minus 8 over 3 minus a negative 8 here, so that's going to be plus 8. And then here it's negative 2 the whole cube, that's going to be minus 8. That minus with this minus will be plus 8, but you have a minus outside, so that's going to be minus 8 over 3. So it's basically doubling the 2. 8 plus 8, 16, minus 2 times of 8 over 3, so minus 16 over 3, which comes out to be 32 over 3. Okay. So this is part A, where we did it with respect to x. So I'll say with respect to x. Now let's do part B, and that will be with respect to y, and we know that we should get the same answer, right? So here again we need to do the limits of integration. For that we have to rewrite our x and our equations in terms of x. Y equals 3 minus x squared, which we have to rewrite in terms of x. So x squared will be 3 minus y, therefore x will be plus or minus root 3 minus y. So if you go back to our graph, it is basically your, this parabola is kind of split into two parts. Okay, the left part, which is negative root 3 over negative root 3 minus y, and then the positive root 3 minus y, right? So it's kind of this and that. So this part would be the positive, I don't know if you can see, yes, positive root 3 over root 3 minus y, and this left function would be negative root 3 minus y. Okay, the bottom one cannot be rewritten as x. Okay, but we do know that the bottom limit c equals negative 1. We need to see what this top limit is, then we'll get our limits. Okay. So this gives us this is our right half of the parabola, and x equals negative root 3 minus y will be the left half of the parabola. Okay. And in terms of limits of integration, we have c is, the bottommost is negative 1 from y equals negative 1, right? That's the bottommost. You see the shaded region, that's the bottommost part of the shaded region. What's the topmost part of this shaded region? That's basically your vertex, right? Where does the vertex occur? So you can clearly see that the vertex will occur where, meaning you're trying to find the y value when x is 0, right? When x is 0, the y value is 3. Plug in x as 0, so y will be 3. So your limits of integration is y equals negative 1 3 minus x squared when x is 0, because that's where the vertex is attained. So c to d, right? So your area will be c to d, right function minus the left function dy. And so that's going to be negative 1 to 3. The right function was positive 3 minus y, minus the left function was negative root 3 minus y dy. Negative 1 to 3, root 3 minus y, that will be a plus root 3 minus y dy. They are like terms, so same term added twice. That will be 2 times negative 1 to 3, root 3 minus y dy. Okay. Now in order to handle this, you have to use the u substitution. So let u be equal to 3 minus y, du will be 3 dy, right? I'm sorry, du will be negative dy. So du over negative 1 will be dy. So that's going to be 2 times negative 1 to 3 square root of u du over negative 1. I'm bringing the negative outside, so it's going to be negative 2. Negative 2 over negative 1 is negative 2. Integral negative 1 to 3 u power half du. I'm going to go with method 2 in that u substitution, where I will save the limits when I replace the u with the x. So I'll use the original x limits. Okay, 1 to 3. Oh no, I can actually do the integration here. U power 3 over 2 over 3 over 2, negative 1 to 3. The 3 over 2 in the bottom will become 2 over 3 here, so that's going to be negative 4 over 3 times. I'm going to use the original y limits, right? I'm going to replace the u with the 3 minus y, I think. Go back, yeah, 3 minus y, power 3 over 2, and then I will apply the y limits, the original y limits. It's negative 4 over 3, 3 minus 3, power 3 over 2, minus 3 minus negative 1, power 3 over 2. So that's 0 minus 4 power 3 over 2. The minus and the minus will be a positive. 4 over 3 times, this we know is 8, right? Square root of 2 square root of 4 power 3, which is 8, and that gives us 32 over 3. And this was our answer from part A. Part A was with respect to x. So again, you get to choose which one is better. I feel like part A was better because it was straightforward. We could use the equation the way it was given to us. But it's nice to see that we could get the answer in 2 ways. So I hope this was a very useful lesson for us, because we're kind of finishing up this course, and so chapter 6 is the last chapter, and so you're free to use all the techniques you've learned before. And so in the next lesson we'll be able to focus ourselves in integrating with respect to x, with respect to y, and developing this area into something called volume. So we'll get to that, but I'm glad that we went over this together, and I will see you in the next video.